Okay, we're going to continue in this class on Newton's laws and connected particles. At the end of the last class I asked you to look at which systems would have equal accelerations here. So I know something here, so I'm going to actually just write in the accelerations of each one and check did you get it right. So I'm going to just write in the acceleration. So you should have gotten the acceleration here would have been 8 over 24 g, which reduces to 1/3 g, or maybe g over 3 depending on what you wanted, how you prefer to write it. So the first one, g over 3 meters per second squared. If I look at this one where they also differ by 8, if you found this accurately, you would have found 8 over 16 times g, which would simplify to half g, or g over 2 meters per second squared. So notice, even though in this diagram and this diagram the difference between the masses is 8 kilograms in both of them, that does not mean the acceleration is the same. If I look over here at this second diagram, what you should have found was the acceleration was 4 over 12 g, which would reduce to, again, g over 3 meters per second squared. Notice that is the same as the first one. And if you looked at this one, you will find that the acceleration would be 2 over 6 times g, which would reduce to, again, g over 3 meters per second squared. And if you looked at this one down here, you'd find that you would get 1 over 3 g, which is, of course, g over 3 meters per second squared. So all of those four, here 1, 2, 3, 4, all of those four have the same acceleration, will have the same acceleration. So what do they have in common? Well, if you look at all of them, the ratios of the masses are 2:1. And that's really what is going to determine the acceleration of the system. This one up here, number 2, those two masses differed by 4. If I look at this one where the two masses differ by 4, you will find that the acceleration, if you work this out properly, will be 4 over 20 g, okay, which will work out as g over 5 meters per second squared. So if you go through all your basic steps, your force diagrams, develop your force equations, that's what you should have gotten. Okay, so where am I getting that information from? How am I doing that kind of thing in my head? Well, let me very quickly go over a kind of a general thing. If I look at these two, this where x is greater than y, again, I'm going to just stick the forces in here. We've got tension pulling up on each of them. Pulling down here, we've got xg. Pulling down here, I've got yg. That's the weight, the mass times gravity. Again, if we think about it, we think that x is greater than y, so the x mass will accelerate downwards. The y mass will accelerate upwards. If I draw my force equations for each of those, for the x mass, down positive, so we're going to have xg, subtract up negative, that t is going to equal to m, the mass, x, times the acceleration. Looking at the second equation, which I'm saying is up positive for the second particle, the tension here will be my up force, my positive force, minus the mass times little g, yg, and that's going to equal to y times a. And just like before, if I add those things, the t's will cancel. I'm going to factor out the g also, so what I'm going to get is g times x minus y is equal to a times x plus y, factoring out an a on the right hand side. So solving there, you can see that the acceleration for a system of this particular type will always equal to x minus y over x plus y times g. Okay? And that'll be meters per second squared. So the difference between the masses over the sum of the masses, that's how I was getting these answers so quickly. You know, that's just a piece of information. I know difference here is 8 over the sum of 24. That's just something that I know. Okay? A kind of a fact that I know. It's not a fact you need to know. You can work all this stuff out just using force diagrams and force equations. Which means if I work out the acceleration of this one, well, the difference between the masses would be 2x subtract 2y, and the sum of the masses will be 2x plus 2y. Again, factoring out a 2 over 2, or dividing the top and the bottom of the fraction by 2. Again, I should have said that's times g. That's the same as x minus y over x plus y times g. So even though I've doubled the masses, the acceleration has not changed because the ratio is the same. And it's not just for doubling. I can prove that for any constant multiple of x and the same constant multiple of y. If I look at the acceleration of this system, the difference between the masses cx minus cy divided by the sum of the masses cx plus cy meters per second squared. Sorry, I've left out my little g there. Times g meters per second squared. But again, the c's will cancel here, dividing top and bottom by c. That's going to reduce to x minus y over x plus y times g meters per second squared. So the ratio between the two particles for systems of this type determines the acceleration, not the difference between the two particles. It's the ratio. Okay? It's the ratio. So check those out, practice some questions, see how you get on, and I'll move on to slightly more complicated problems the next day. Don't forget, as you're going along, any questions that crop up, make sure you send them to me, and I'll try to go through them during the live lesson. Okay?